I'm going to give a brief introduction about what is WebAssembly and what is zero-knowledge virtual machine that supports WebAssembly, and how these two can be integrated together to bring us new paradigms of coding new Web3 applications. And in the second scenario, I would like to introduce our architecture purely designed for web gaming development. And in the third section, I'm going to demonstrate how to develop a client-side full on-chain web game using our WebAssembly virtual machine by developing a game from scratch. And in the fourth section, I'm going to introduce a little bit more about how to extend this architecture to support client-server architecture. And at the end, at the fifth section, I'm going to introduce about the proving service, 2 layers of proving service, and building primitives, and storage, and random generation, etc. And in the end, I'm going to show you the proving service and discuss a little bit about the privacy when you're utilizing a proving server. Okay, let's start. So, section 1, the brief of WebAssembly and WebAssembly secure emulator. So, I'm going to show a diagram like this. This is a diagram that I stealed from a pitch from the WebAssembly edge. So when I introduce WebAssembly, these guys always discuss WebAssembly. Sorry? Okay, it's too small. Because I need to alt-tab a little bit, so I'm not sure. So let's see.
Slideshow.
Okay. So okay. Is that clear now? Okay, I steal this graph from the WebAssembly edge. So they put an emphasis on how good the WebAssembly is by showing that there are lots of applications, the frameworks can run on the WebAssembly virtual machine, and the WebAssembly virtual machine now becomes a standard for the browser applications, because now you can call WebAssembly application APIs from pure JavaScript, TypeScript, and you can run the application in an environment like Linux, Mac, and browsers, and even SL4 RTOS. And it can become the back end for the majority of the languages like C, C++, Rust, Swift, and Kotlin. And there's some acceleration about this JavaScript and Python because as far as I know, at this stage, there's no translation from Python or JavaScript to WebAssembly. But the WebAssembly can be generated from assembly script, which is very similar to JavaScript. It's called another version of TypeScript. So that means WebAssembly is kind of very popular to support various generic languages. So this is also the host APIs that built in the WebAssembly can be used to integrate with lots of language extensions. So in conclusion, I think the Wasm edge trying to sell the WebAssembly by telling that the WebAssembly bytecode is kind of awesome, right? And so now, because it's awesome, and but it's not used by Web3, right? So we try to actually leverage the awesome WebAssembly bytecode by providing a zero-knowledge virtual machine that supports the WebAssembly bytecode. And so last year I gave a talk at ZK Proof talking about the architecture and arithmetic of this virtual machine. So I'm going to skim this a little bit and just show you that it's a circuit architecture, right? With this architecture, you can encode in the WebAssembly semantics in Hello 2, right? So, which is our arithmetic backend. So when we implement this WebAssembly virtual machine and support all the instruction formats except float point, then we are happy to say that we have the ability to leverage the WebAssembly bytecode by running WebAssembly applications in our Wasm ZK virtual machine. Right, so that gives us a way to connect the awesome outside world of Web3 or Web2 to Web3. Okay, people can check out our source code and our full design of the arithmetic circuit here. So now, we combine this together, right? We combine this. So we have the Ethereum, we have our WebAssembly virtual machine. We put the application in it, and the application becomes an automatic roll-up for the Ethereum, and it runs the native WebAssembly bytecode. And by running the WebAssembly bytecode in this our zero-knowledge WebAssembly virtual machine, it generates proofs, and proofs somehow delegate back into the Ethereum, so we can do some settlement here. Right, so that's the architecture. And today, I'm not going to introduce all the SDKs that we have for the WebAssembly, but I'm going to introduce our game SDK, which is called Lorana. So that using this SDK, you can code a small game, and run that in the browser, and talk with the Ethereum, and also get information from the Ethereum from a CK relay that's provided by some of my friends. We will introduce these friends in later. Thanks to them. Okay, so now this is a brief about what is WebAssembly ecosystem and what we can do with the WebAssembly CK virtual machine. Okay, now let's dive into the game. Before I start coding a game, I'll give you a brief about why game is kind of a very key scenario that we are going to target. The first of all is that I'm going to introduce how the game is currently coded in Web3 world. So some guy tells this kind of architecture to be Web 2.5 because the game engine is running outside the chain, right? At a certain stage, some kind of participant triggers a job. So it's not a transaction. This is not a transaction. So Ethereum or blockchains are transaction-based, but it's job-based because it can interact with different users in this game. So in this job, at some stage, it will actually communicate with the unchanged data to maybe, do some transfer, mint NFTs, and sometimes, do some penalty calculation. Yeah. And so the problem of this, the advantage of this architecture is that it's very efficient. Right? If you want to change or upgrade the game, it's pretty easy. You change the key path, right? At a certain stage, you change the on-chain data. But it's not very secure. Just imagine that you have an NFT that last night it was maybe 1 million, but after that, someone changed the logic of the game, then your NFT was nothing, right? So it's not very secure, both for the game and for the users who play that. So this is called Web 2.5 gaming engines. Okay. And now, so where is this? There's no title here, sorry. I think there's an animation coming very soon, but it's a little bit delayed. So here we're talking about that to secure, so we still have the same thing for 0.1, but to secure the outside logic of the gameplay outside of the blockchain. So people can encoding some of the logic into CK circuits, right? So with a CK circuit enhanced architecture, we can say the data modification is triggered by a successful verification of a proof. So in the contract, it verifies a proof and shares some kind of the convention with the inputs, and then do the settlement, right? So this architecture is a big improvement of the previous one, but the problem is that it's very hard to reason about whether the semantics of the circuit is exactly the same of the semantics of the game, right? You have a game, you have a circuit, and you want to convince people, if the circuit's constraint is satisfied, then the game is somehow run in a same manner, but it's not very easy to prove, right? You have to do lots of auditing, and you have to check the circuits, to check the constraint, and every time, in particular, every time you upgrade the game, you still have to upgrade the circuits, right? So that is a fairly popular architecture. I think maybe we need to go, right? But now, once we have the zero-knowledge virtual machine, things changed because we can imagine that this gaming block is not building in traditional language, but building some kind of bytecode that can run on a virtual machine. Or you can replace this, our virtual machine with any virtual machine like zkVM, RISC-0, any virtual machine. So the benefits that usually if you have a virtual machine, do not have to reason about that the semantics of this is actually the semantics of the initial game engine, right? But the problem is that, so if you have this kind of architecture, the upgrading is not that easy because every time you're upgrading the game, it generates a new hash for the image, right? It's not very easy to upgrade. And there's other problems when utilizing this architecture. It's because when you, so for example, if you imagine that you have a game that developed on a browser, right? How could you interact with this game machine? So if you have maybe, so for example, Carrier virtual machine, then you have to actually install the Carrier virtual machine in the browser, right? You have any kind of virtual machine, you have to install the virtual machine there so that you can make sure that every transaction here actually follows the bytecode. So the problem is that the integration effort will be a little bit higher than before because everything returned here is the target bytecode that you are going to interpret in the virtual machine. So to solve these problems, because we are currently focusing on the application, browser applications, so we replace this virtual machine bit in the architecture by a WebAssembly virtual machine. That means we load the WebAssembly natively in the browser, right? We interact with them, and after that, we using the virtual machine to emulate the bytecode, and then we upload our proof to the blockchain and then to the settlement. But now, it still remains us two problems. The first problem is that it's not very easy to upgrade. It's not very easy to upgrade. And the second problem is that because the virtual machine takes a lot of time to actually generate the proof, so that means we cannot support very high TPS games. But I'm not going to solve the problem today. So in the rest of the talk, I'm going to show you how to leverage this architecture and build a game. Okay, let's build a game. So I need to put the Mac down because I need to type in. Okay. So I'd like to thank for the guys from the zkCross team to develop this game for me. And the game is pretty straightforward. It's a GU 2048 game. So that means you have a game, you move the blocks, you combine the blocks to generate a larger block, and at the end you have some kind of rewards or some kind of mark. You can upload the proof of the whole transaction of the game to the blockchain, and then get it. Right. And let's look at the source code architecture. Okay. So let's start with this. This is a purely game coded C, right? So nothing special here. And once you make that, it generates WebAssembly. It generates this WebAssembly. Looks like. Oh, okay. Well, that's bigger. Sorry. That big enough?
One more.
One more. Okay. Good. Okay. So that means you write a program, you just compile that using our Lirana game SDK, and then you generate a WebAssembly. So what did you do with the WebAssembly? You can run our WebAssembly virtual machine locally via CLI, but you can also using using a proving service. Maybe it's a WebAssembly virtual machine proving server. So you upload the WebAssembly straight through this WebAssembly virtual machine, right? You upload that. Then after you upload that, you can maybe trigger some tasks to do the proof. But now I'm going to do that step by step. So now I have upgraded that to the WebAssembly virtual machine online service. That means you have established an application, right? You can establish an application locally. You can also establish application on our online service, but it's not very important. So once you have done this, you see that it is very natural to actually load the WebAssembly into our gaming execution environment. here you import the WebAssembly here. Sorry,
Is there a GitHub repository? Is there a GitHub repository?
sorry?
Is there a GitHub repository?
Oh, you want to see the GitHub repo or? So I didn't get what's the question, sorry? Sorry, I didn't get.
The link,
It's open source.
the name of the repo.
That's open source, yes, open source. Everything here is open source. So.
He wants the name of the repo.
The name of the repo.
Oh, you want the name of the repo? Okay. So that it has. Okay. So the game is provided by CK Cross team. The game repo is here. Game repo is here. But the SDK repo is in Delphinus Lab, so you can download the SDK and copy that code to make a new game. Okay. So now you have this. You load the game, and then you provide some kind of environment that you cannot make a circle for that because the abort requires the table memory kind of memory is just doing the circuit, but you delete the abort. That requires not kind of a standard function in the JavaScript environment. So providing them, and now you have generated WebAssembly. You have uploaded that into the WebAssembly proving service. You're loading them, and now it's time to play. Yeah, so now generate a game. So in this game, it's just a 2048 game. So the idea is that every time you press the button, top, down, left, right, it get inputs into the WebAssembly, right? Get inputs into the WebAssembly. And so this becomes the private input, right, for the ZK system, for the WebAssembly virtual machine, because you do not want others to know how to play this game to maximize the currency, right? You play that. You play a little bit. So in a standard Web 2.5 setup, you probably have to interact with the blockchain every step you do, right? You press a button, you sign that. You press another button, you sign that. But because this is a zero-knowledge virtual machine, right, you do not have to do that. You play for a while. So usually I play this game for about 1,000 steps. And I found, okay, it doesn't work. Then I give up this game. And I start all over again until I find a way that I get some good results by very good move and by selling some good stuff and to get some currency. And once you're happy with the gameplay, you can generate a proof. I mean, here are the proofs that I tested last night. So now I'm going to generate one. Submit a proof. You see that, okay, we have 8 steps, and we somehow putting everything in a sequence, right? So we feed the sequence to the WebAssembly virtual machine and to redo the execution. And this time, the execution not only gives you the result, but also gives you the proof, right? So I'm going to submit that. Okay, confirm. Sorry, usually you do not have to sign, but because I'm doing a good demo, so you get a pending task, right? So, and this is now doing on a non-GPU machine, so it will be a little bit slow. So just imagine that we have submitted a proof that actually proves that a sequence is very good. You can check the proof here. With this instance, you have this kind of lots of proof scripts and some auxiliary data. So I'm going to just introduce a little bit about the proof that we generated from the, sorry.
What are you proving?
I'm proving that actually with all my transaction inputs, I get the currency here. Sorry. Let me show you. So I get the currency here. 22.
So you're proving that your sequence is...
So that proves that this game reacts to my gameplay sequence. It gives you this currency. I mean, but you can code in your program in your logic, right? But here, this C program is coded like have an input of sequence and then you generate what you need. Okay, right.
Do you actually store all sequence by side? Or you just store the state?
code. The idea is that you do not have to if you look at the C code, you see that the entry of this function, right, is by completely read from the command block, right? So there's a command. So every time you interact with the game, then you generate a sequence of inputs, right? Before we have some kind of simulation functions implemented in C and loaded in JavaScript, and in the end you just encoding all the sequence and put that into the zkVM. So that zkVM actually generates what you will get after playing like this. Oh, sorry.
Your zkWASM, do you have like support to like some standard library functions like giving memory?
Yeah. So everything except float point.
Everything except?
Float point. So, and we're not going to support float point. It's too hard, right? It's just too hard. Yeah, maybe some open source guy will contribute to the float point, I will expect, but currently I'm trying to just push the boundary. Okay, so now you generate proof. So last time you generate proof fails for, I don't know what's the reason, but maybe it's not stable, the testnet is not stable. Someone maybe also using the testnet board. But now, once you actually have the proof transcript and the instance, I'm going to introduce a little bit about the instance and the proof. So the proof is constant because we're using Snap in Tolo 2 with privilege commitment. So the proof transcript is kind of constant. We have this auxiliary data because we want to cache all the inverse of the field so that we get less feed on the contract. And once you do the verify on chain, it asks you to actually pay a little bit gas. So the gas fee looks like this. It's still expensive for this very small game. It's super expensive, $10, right? But eventually, if you have a batching or aggregation service, you can reduce the price. And because it's constant proof size, so I think in the future it won't be a problem. But also currently in a testnet, it's also not a problem. Okay, let's reject that. I don't want with my test token. Okay, so now let's recap. Oh, sorry. It's Hello to Okay, let's recap what we have already done in this section. So we introduced how we cache the steps, right? And then we generate a sequence. And we have introduced how to load the Wasm image. We have introduced how to load the Wasm image model, and the gameplay, the proof. And now, let's back to the settlement. Because once you generate a proof, it does not actually instantly pay you back, right? You need some kind of conventional protocol to do the settlement once the contractor verifies the proof. And here I just given a very simple example about how you can actually design your convention of payback. You can design a contract. There's a report here. So in the end, I will share all the reports that you need to actually create this. So basically, you write a contract at entrance, and then you verify you cause the contract in our service, right? So basically, you can call a contract in our service. So for those who actually get a very good deploy, let's see whether, so for example, if we have a look at this image, you will find that, okay, this image is deployed at this address. So that means when you design the settlement contract, you call a verified contract that is related to your application. You give them all instances of proof and auxiliary data. If that succeeds, you can design your convention about, okay, what bits or what part of the instance tells how much token you have to transfer, how much NFT you have to mint, or how much penalty you would like to charge. It's basically, you can design convention for this. And then obviously, because you want to do some big game, you always would like to pin the state of your multi tree in content. So the update state, you perform transfer. So there's one thing that you have to remember is that if that pass verification, just make sure all your settlement will not fail. It's all in your control, right? You run it properly, it's fine. Okay. So now, we need to dive into a little bit about the hard part of the gameplay because in previous section we were only talking about small games running standalone in the browser application. But in the real world, the game does not only run in the client, it also runs in the server. So how could we make a uniform architecture that not only support the client, but also actually support the server? So we need to actually provide an infrastructure that combines the client and the server. And because we're dealing with WebAssembly, we can encoding the RPC in WebAssembly remote call. But the remote call can be now encoded in the host function. In the WebAssembly, there's a function category called host functions. The call host function is equal to call a remote function that is provided by the host. So now we can split the architecture of the WebAssembly virtual machine into two parts. The first part is the guest circuit, and the second part is the host circuit. Right, okay. So within this architecture, all applications can design their own circuits. We have an SDK of host circuits they can use, but they can develop their own host circuits. And every time a client-side WebAssembly calls an RPC, you can think that as calling a host circuit. It gives you the witness in the front end, and you can generate the proof for the guest WebAssembly virtual machine. Okay, it's a little bit tricky here because once you generate proof for this WebAssembly guest virtual machine, you actually do not prove that the host call is somehow valid, right? You have the witness for the host circuit, but you did not actually prove the host circuit is correct. That means the backend side needs to prove the sequence of the host call is correct using a host circuit. Okay, and this looks like this. Okay, so we have split the virtual machine into two parts. The first part, I'm going to show the code, so if you're missing anything here, it's fast. Just get some idea about this. This guest execution, it has a host API, right? The host API actually takes in A and gives you B. So in Hello 2, we're somehow encoding this in a column, right, like this. So that means every time you execute this, you define the semantic of this by a lookup argument here, right? And then you hash this to get a hash. Now, in the host circuit, you give them the same column, right? You hash that this circuit also proves that the hash holds. And then in this host circuit, you prove that the host of code to 1 actually generates B if A is the valid input. Okay. So now we have two proofs. We're splitting them. We have a guest proof, we have a host proof. And then you just call in our batch service. Actually, we call a batch proof. And in the batch proof, we prove two things. The first thing is that this is a valid proof, and this is a valid proof. And the second thing proves that these two proofs share the same host for sequence by checking the hash. Right. And that means combine these two, you get a server-client architecture. Okay. This bundle proof, I think I've already explained this. This is just trying to concentrate and emphasize the aggregator will need to make sure that the hash is safe. Okay. So now let's talk about the common primitives in the host circuit. So basically, we only provide minimum host circuit APIs like user signatures, EM250, 4 and EL381, verify randomness, task primitives, that's for sure, and some kind of attestation. This is provided by Programmable, which gives us our ability to get information back from the Israel. So that means in our game, we can listen from the Israel by this attestation host circuit. Okay. And all the common primitives are implemented using much more atomic primitives. So if you see here, the multi-signature using 4, storage using the hash, and the randoms using 3, and yeah, so it's nothing special. I think all the zkVM implementation have this. And okay, let's see a little bit more about the attestation primitives, because this is the whole circuit that we can listen from the Israel. Make a program with WebAssembly, virtual machine, and then waiting event from Israel by calling this whole circuit, like to try to, this is the yes client code. We'll attest an event, waiting here to attest an event, calling the RC call. So if the whole circuit gives you okay, the certain event happens on the Israel, then you go through all the logics and then generate proof. So this is a standard combination of an attestation circuit and the guess circuit. With this, you can develop some more sophisticated games that not only talk to the Ethereum, but also receive information from the Ethereum. And this is kind of the attestation. I just want to emphasize one thing. So this is not an attestation of the global data structure of Ethereum. It's just an attestation of the secret. To prove that on certain received hash, certain event actually happens. Right, so this is it's a special circuit because most of host circuits is actually carried on the server, right? But this kind of host primitive circuits is that provided by some server by monitoring the Ethereum events. Okay, I'm talking a little bit quick. So the last section is the privacy and the proving service. So I have actually already showed you the proving service. So it's kind of very easy to manipulate. So you will write any program and you build it here. Oh, sorry, am I out of the internet connection? That button doesn't work. It's an online service. I think there's some internet problem preventing me downloading the binary, but yeah. So once you get a binary, you create a new application, you choose application, upload that, and generate a new application. But within this framework, there's a majority problem that we face is because the proof is delegated to the proving services, all the witnesses are leaking, right? So you will play some kind of card game. Right, so that means maybe the server see all your cards, or maybe some other one that hack into the server, proving server can see all your inputs. Okay, so I think there's actually a big problem of actually delegated proving to the prover node. This is the cloud improving service. So let's figure out which bit is very risky and which bit is not. So for the applications, you can calculate the witness here, then save. If you're sending anything to the task database and provide the witness, then the witness gets fetched by the guest server prover, right? The guest server prover. You can imagine that the guest server prover is a proving service hosted by the game supplier, right? So this is kind of a little bit risky because, but you can still trust the centralized gaming provider. But when you actually delegate the service, proving service to some kind of host circuits, right, that means this kind of circuits will be proved by decentralized provers and the witnesses are leaked. Right? So this is very risky, this is less risky, and what we prefer is that we can prove everything in the client side. But in the current Hello 2 setup and the current implementation of Hello 2, of zkWASM, it takes more than 20 seconds to generate proof and do a batch together. Right? So it's not feasible in our architecture at the moment. We probably benchmark this and push the performance a little bit harder. But today I'm going to introduce two ways to solve the problems of delegating the proof to different provers. One is published here. I'm not sure whether I get all the ideas from this paper, but I think there's a less complicated solution in that for all the columns, we generate a random polynomial, right? And then you have polynomial A, which is the initial polynomial, and you plot that with a random polynomial, and give the witness separately to two provers. And these two provers calculate and make an verification and sending back to the user. So I cannot say that I fully understand this, and we are not implementing this yet, but just to give you something about actually this can be done. And the complexity actually increased by a factor of 2 according to this paper. So, but we actually haven't implemented this. What do we implement? So we implement a way to preserving the privacy by implementing a prover in the zero-knowledge WebAssembly virtual machine. That means if you want to type something, right, you can create a circuit, verify the statement in your private circuit, and generate a proof. And in this WebAssembly virtual machine, we implement a function called post16 verify. And you can upload the witness of this verification proof so that it gets circuit proving the statement without knowing the actual witness. And this is done, I think you can find the embedded proof implementation here. And the idea is pretty simple. For example, you want to prove that you know two numbers that multiply together equal to a very large number. But you do not want to actually leak the information that you know the two numbers, right? To implement that, you, okay, so let me show you the code. To implement that, you somehow create a circuit. It's a circuit, right? And you compile the circuit, get the setup, and then after that, you use the setup to generate a verify lib to do the verification in C code or any code that can be compiled into WebAssembly, right? So that means you can use the CK WebAssembly virtual machine proof without actually leaking information that you know the two numbers that multiply together equal to a target number. And this technique can be used on anything that you want to hide. And we are going to supplement actually two verifiers. One is the growth 16, and the other is the Plonk. So there's remaining another problem is that if you look at this code, you find that you need to calculate a pair of 4, right? So even in our optimized Hello 2 circuit, you do a pairing of 1, proving a pairing of 1, and write a pairing circuit which will take you 16 seconds with one GPU. So you want to do 4, there are lots of overhead. But we will somehow optimize this. But currently, the fact is that even if you want to choose this approach to hide the information and provide privacy in your zero-knowledge WebAssembly, then you are running the cost of 20 more seconds batching. But I think for small games with very low TPS, if you're in a gaming or gambling or some kind of game, 20 is fine. But I'm not sure. But currently, that's what we have. Okay, I think, yeah, that's all about it. And I would like also to give the partners that provide me all the code there for the demo. Thanks for everyone. If you have any questions, please let me know.
Yeah, right. It's like when you block, like that game
you're using a signature. It's not proven by something random. At the game, at the beginning of the game, you pick something from your last and then you sign that. So you move top, you appending one. Let's suppose that one is for the common root. Appending one to your root node, and then sign it. And then signature, and then generate the next. So it's not a perfect random, but it's just for demo. So if you have two players, you probably ask them to sign twice to generate the proof. But yeah, it's not a very sophisticated random generator, but that's what we have for demo.
So in the second part, initially what you're doing is in the guest code you're putting the inputs for each move, right? You're generating the proof for all of those, and your solution to hide the inputs is to generate the proof for the proof generated for all of the previous moves, right? And what's the input? So the input for that second proof is the proof, the previous proof itself.
Except the private.
Except the
L plus some of something. Yeah, basically, yes.
And how long does it take for the second proof to?
The batching is kind of a bit long at the moment. We're using this whole circuit like carrying and
20 seconds.
we're not using carrying anymore. But I bet we will need to use the carrying signature because we're using the carrying to generate the revenue.
Right.
So currently the benchmark is not very ideal, but if you want to write something that's much simpler, then it can be very quick. So if you want random, sorry, it's GPU. It's not as good. And it's also 4090 already, so we definitely need to improve that.
So maybe I can get how many Wasm cycles does the virtual machine prove?
Oh, okay. So you want to know the certain site for program.
And I'm asking like the prover on GPU, how many Wasm cycles does it prove per second?
It's not proving GPU is not water cycle. We implement our virtual machine that supports WebAssembly, but do not turn the prover to WebAssembly.
One last question. Where can we find the SDK? I would like to run this, and I'm wondering where I can find the SDK.
Oh, the game is so. If you check out our GitHub, there is. I'm not sure. This is a very. You can see the game here, but not very up to date. I'm going to upload everything to the. Oh, sorry. I'm going to upload everything once I finish the talk. But you can find the sketch provided by CK Cross team.
Any chance we can build the game, or right now it's only you can build it?
You can build it's everything you can download from source code. But
Sorry,
yeah.
I just don't know where the SDK is. I cloned the repo for the game.
Yeah, you can search zero knowledge WebAssembly virtual machine and open this repo.
Yeah, and I cloned that too, and I copied that clone into the folder.
Yeah.
And it's not finding the build.sh script.
Oh, sorry, I didn't get the.
Yeah, we get it. Throw it.
Okay, so yeah, I think that's for today. Thank you very much for attending. Thank you.